Thanks so much for having me. I'm excited to share some recent and not so recent experimental data with you that deals with ice friction under dynamic loading conditions. And so although I have worked a little bit on some other materials, primarily my favorite of the materials is ice. I've been working on it for a long time, studying a lot of different material properties over a range of time scales and temperature, space. And today, though, I'm going to be talking, I'm going to be focusing more on this end of homologous temperature space where ice on Earth tends to live. So this very high homologous temperature. And so I'll be sharing some results from friction experiments that we use to try to understand glaciers. But really at the heart of it, I do try to see the world in kind of this homologous temperature space where, ice is just one of many materials that should behave according to specific rules. And so that, things that I learn here in this wide range of conditions, maybe overlap with the behaviors of say, granite in the Earth's crust or olivine deeper in the Earth at higher temperatures. And my hope is that, one system can inform the other and vice versa. And I guess also at the heart of it, even though I've studied a lot of different material properties, it comes to the fact that I study how a chunk of stuff, when deformed and experiencing external forces, how it responds. And in particular, I really liked thinking about how all of these little defects and attributes at the grain scale, how the micro scale affect the macro behavior. And in particular, for today's talk, I'm also thinking of how the external forcing, so the time, the frequency, the velocity of the forcing affects the response. So that's some of the things that we're covering. And again, I think about how these micro things affect macro behavior here and elsewhere. And in particular for the ice here, which we know is fleeting, and I'll admit that some of my probably my references are a little out of date, but it comes as no surprise that the threat of sea level rise is real and worrisome. It creates a grave threat for dense populations near the coastal cities. And so in order to improve planning and infrastructure, being able to model this is important. And I am not someone who focuses on these kinds of models. They seem very complicated and involve a whole lot of inputs. Rather, my research, I hope, is providing, one small puzzle piece that might shed light on how this effect here, how the melting of land-based ice, how rates can contribute to sea level rise ultimately. And there's a lot of variation in the rates by which ice moves around from land-based ice out to sea. Big variations in velocity from nearly stagnant velocities at the divide here. This is Antarctica, out to incredibly rapid velocities of the ice shelves. Because these are not grounded, and so they're being pushed pretty freely. But in particular, something I'm interested in are what are termed ice streams. So these are relatively fast-moving streams of ice. It's shown here in yellow, that are going from the divides out to the sea, and they're called ice streams, and they show a lot of variation as well. And so the things that control this in this very simplified cross section, how the rates by which ice would go from accumulation areas out to sea. There's quite a few factors. Certainly at this high homologous temperature, you're going to have viscous behavior within the ice. And that is for another talk. I'm not talking about that today, but certainly that is important. Rather, you also can have in these ice streams sliding at the base. And definitely for decades, this has been explored, and it quite often is described by viscous approximations. And that's fine, particularly if the scale by which you're thinking about this process is long term. However, there's a handful of features, which I will get into in more detail in a bit, that suggests that this could also be examined as a frictional process. And in particular, my background was in ice, but when I arrived to Lamont, this is one of the birthplaces of rock friction, earthquake mechanics. And so we in our lab wanted to approach this project, this phenomena, as a frictional process. And in the past, the classic view was that either, if the temperature at the base was above the pressure melting temperature, then you've got a layer of water and it's just slip sliding away. Or if it's above the melting temperature, below the melting temperature, it's stuck. And so sort of kind of an on-off approach to friction. And we thought, well, maybe we could provide some additional information. And so when I got to Lamont some 11 years ago, we thought, let's study ice friction. We were not the first to think about ice friction. I will not try to say that we were. For many, many years, there have been people, be it motivated by winter sports or automotive safety. The study of how things slide on ice has definitely been well studied. And described as sort of this continuum between at really, really low velocities, creeping at very high velocities, sliding on a thin film of melt. But it was in this in-between range of velocities. These are the ranges that glaciers and ice streams move at. And so we wanted to kind of dive in a little deeper to this area of the frictional behavior of ice. And so we designed a rig. We designed this rig based on the classic biaxial apparatus that has been used for many years to study frictional properties in rock. But we kind of, as we sat down to think about it right from the get-go, we realized it didn't have to be so big and burly as the ones that deform rock. Ice has a modulus that's, an order of magnitude less. And so we could make it a little bit more airy. And in particular, what we really wanted to do is to have a lot of daylight here where we can build a really nice cryostat to control the temperature for long durations of experiments. And in particular, we followed many old rock deformation experiments in using this configuration called a double direct shear configuration. So in this, you have 3 blocks. The 2 side blocks, in this case, ours were rock, are stationary, held up by blocks of steel, and the central piece of the central sample is ice. And in this case, so these are squeezed together horizontally, creating a normal stress. And then we use a program to control the velocity, the downward velocity with this piston. We control in velocity, and what we're measuring is, with our load sail here, is we're measuring the shear stress that's felt along these 2 interfaces, such that friction, which I'll be showing in all of these figures, is the shear stress divided by the normal stress. And so we designed a rig, and then we built a rig. So we did it all in-house. I was a postdoc at the time on a kind of a shoestring budget. And over various stages of pregnancy, we built this thing. And it was trained a lot of undergrads and grad students and postdocs coming through the lab. So it was a really great experience to build your own lab from scratch, or own rig from scratch. And furthermore, I decided to use sort of the philosophy that I had learned through my PhD about, making very reproducible samples. And so we've got a walk-in freezer, and we make all of our ice samples this same standard ice method of sieving and flooding, and sieving and grinding and sieving and packing and flooding, so that we have samples that are identical every single time, unless we systematically want to change something, and then we do. So kind of following this philosophy and following the footsteps of rock mechanics folks, we embarked on our study. And in particular, I guess our sort of niche or our contribution was that we wanted to use the same formulation that had for decades been used to describe earthquake physics, to use that on this ice on rock system. And so this is a rate and state friction law, where, many years ago it was observed that the friction is not just, first order response, you also have second order response where it depends on, the velocity that it was at, if you have a velocity step where it goes from one to the next, the velocity it was at, also it depends on state, this characteristic of the interface. And I don't want to go into too much more detail about this other than to show this one concept that in particular that rate and state friction is valuable for, and this is to talk about stability. And so there's these A and B terms, which you determine in the laboratory by doing a velocity step. So I would be chugging along at some slow value. It's like our velocity is kind of up here. And this is what our friction is doing. It's having some steady state value. And then I increase the velocity, and there is a direct effect in the friction, it spikes up, and then it evolves eventually to some new value. Now, whether or not that value is up here, higher than the original friction or lower is really important. So this relative size of A and B, such that when A minus B is positive, this is called velocity strengthening, and this is a system that's not going to have earthquakes because the fault gets stronger as they slide, versus as it's shown here, where A minus B is negative, this is a system where it's called velocity weakening, and they might be able to have earthquakes or stick slip events. I'll return to this strengthening versus weakening, VS, VW, quite a bit in this talk, so I wanted to spend a few minutes on that. And what this looks like, I guess, sort of in nature and in the lab, it's very similar to, sort of this conceptual process of having a slider block, some just big block, and a spring attached, and you can pull this spring along, and this block can get stuck and then at some point lurch forward. So this would be a stick slip event. And what that looks like in our experiments is stress, which is proportional to friction, would steadily increase and then would plummet, and then steadily increase and then plummet with time. And what that might look like in nature then, if we're looking at instead position, you would see that for some amount of time, the position would be relatively constant, and then it would lurch forward, be kind of stuck for a while and then lurch forward. And so we were motivated to use this kind of stick slip analysis because there is at least one ice stream in Antarctica, Willen's ice stream, that part of it is exhibiting this kind of behavior. Now the sliding portion, I think, occurs over about a half hour. So one could say that it's more like a slow slip event, but still it's having this behavior at one part. There's another part of that same glacier that is just creeping along steadily. Additionally, people have measured over time, Winbury is where this paper is from, and found that, that as the time between events increases, the distance that it slips increases as well. And this kind of distribution that is similar to what's seen in earthquakes as well. So then it became kind of a holy grail in the community to try to find why this is the case. Why is this one glacier having velocity weakening behavior? It's stick slipping. And so here are a bunch of different kinds of experimental studies. And so what we're trying to find is like the stuff in the gray, response in the gray block. And you can get it perhaps with rock, sliding on rock at some conditions. And so this paper in particular was invoking maybe embedded debris in the ice might do something like this. You can also get this kind of gray behavior with ice on ice at not so cold, just slightly below the melting temperature conditions, but that's not really the scenario with glaciers either. It's not sliding on ice, they're sliding on the ground, whether that is till or rock. And so we're just not finding at the temperatures that folks think that these ice streams are at, which is right at the melting temperature, we're not seeing velocity weakening behavior. So we were kind of motivated by this to try to look for velocity weakening behavior as we embarked on our experimental routine. We followed some of the same types of data collection that has been long run in rock friction studies, that is running a series of velocity steps, up and down in velocity with our forcing, and so that we can examine these little velocity steps for some of that rate state friction information that I was telling you about. We also conducted a series of slide hold slides. So that's where you're basically chugging along at one constant velocity, in this case 10 microns per second, but then you will stop the piston. And so if over here on this inset, shown in time, here you've been having a steady state friction, you stopped the piston, the system relaxes, the friction relaxes for some amount, and then when you restart the piston, the friction jumps up. And it turns out that amount that jumps up, that delta friction, increases the longer it's been holding. So this is a slide hold slide, and that process is called healing, and I'll get to that in a minute. But in looking at our data and evaluating all these velocity steps, for this study that we conducted, which was just a simple ice on rock system at a variety of temperatures, we did not solve that problem. We found that for pretty much all of the temperatures that would be realistic for glaciers, we found velocity strengthening behavior. We did see at lower temperatures a crossover to this behavior, and at the very end of my talk, I'll show more recent behavior. I think this crossover is actually quite a bit lower, but we didn't find that sort of slam dunk for velocity weakening behavior. What we did, though, find is some interesting temperature dependence, where, here are the different temperatures we explored with the simple ice on rock friction system. And if you plot those, friction versus temperature, this is just steady state value, you get a roughly linear dependence in this range. And I'm told that this is useful for those folks who are trying to model, for instance, this complicated bottom of glacier system where you've got margins and maybe sticky spots and things like that, and where the simple convention of on or off is useful to work, or is not so useful to work with, that you want some sort of gradation. What is the transition from friction, high friction to totally melted? What does that look like? So we did provide a curve for that. In particular, what we think about is what's happening at these interfaces, these asperities, and you can think about this drop-off, this drastic drop-off at the melting temperature is due to, I'm not even going to say likely due to, we know it is due to having a melt film, because at the end of these experiments, we saw like a little puddle of water at the bottom. Like, we definitely know that we had liquid at the interface under these conditions, and that it explains the drop-off in friction. We also looked at microstructures. Told you I really am interested in the microstructures. And so this is the cross section right here, like right at the sliding interface. And for those samples above colder than the melting temperature, we saw some elongation of grains or some growing of grains, but generally the edges looked almost identical to what the interiors looked like. So this kind of nice foam texture as we created them. But in those samples that were at the melting temperature, we saw these elongated grains that we know from past experience is consistent with a melting and refreezing. Just to kind of describe now now, if you were looking with the camera, like the same direction as this arrow, if we're looking at that sliding interface, that's what these two drawings are. This was before the sliding, and this is after an experiment. And in all cases, we always roughen the sample on 100 grit sandpaper. You know, we always do it exactly the same way for the same amount of seconds and things. And so this is what the interface looks like as soon as we start an experiment. And at the end, just in case you're wondering sort of what's happening during sliding, we see a lot of the same sort of macro or the larger wavelengths grooves that we've created. They persist. But I could say that maybe some of these sort of low amplitude areas in between. So like if you're looking at this cartoon, you know, that these remain, but some of these sort of low amplitude curvature seem to grow, and you have grain growth at the interface through the course of an experiment. And likely that is due to this healing that I talked about. So I said when we were running these slide hold slide experiments, we are driving along and we hold the piston, it relaxes, it jumps up, and then it continues on. And so the prevailing theory for friction is that during the holds, the real area of contact, so not the entire interface that you've made, but the actual, like all the bumps and asperities and things that are in contact, that they have time to grow, likely some kind of a viscous process at these little high stress concentrations. And so we plot our data as a function of temperature and as a function of hold time here, and you can get a value for what's called healing here for these various ice interfaces, and you can we describe that as a function of temperature in our paper. And similar experiments, different geometry. They had big ring shear experiments out in Madison, where they're looking at similar processes, doing this same kind of a slide, hold, slide experiment. And I just thought this was kind of interesting because I'm just telling you about these sort of 50 by 50 millimeter squares interfaces, but this nice work by Luke and Neil, they are looking at the healing and these big ring shears plotted in black, but they are also looking at the kind of healing you'd have in the field, looking at the field data. And the interesting thing is that, yes, on the scale of just days, ice can heal. You know, I think that folks thinking about rock healing, you know, that they think on a daily scale, a diurnal scale, that doesn't seem possible, but ice at high homologous temperature can indeed do that. And his nice comparison between field and lab work, you know, shows that. So it's nice. So those were some of the effects of temperature and holding. And but you know, as the title of this talk implied, I wanted to look into some dynamic forcing. And so we, you know, motivated by the observation that there are many ice streams in both Greenland and Antarctica, here I've shown Antarctica, that are modulated by the tides. We wanted to try to explore that in the lab. So some of them are modulated by the diurnal tide. I think I really like this nice study of Rutherford ice stream, where, for instance, they have GPS aligned along the center part of the ice stream, where the number denotes the distance in kilometers from the grounding line. And then here is the tide signal. And then up here is, you know, what those GPS were telling about downstream motion when you removed the average value. So this is, you know, about zero because they've removed the average. And you could see in this case, the diurnal tides are actually just kind of like little blips. But in this case, this particular ice stream was more tuned to the spring neap cycle, which is more like a 2-week cycle, I believe. So I find that kind of interesting. But returning to this this Whillans ice stream, I had mentioned that part of it is stick slipping, and this isn't so random. It actually appears to be modulated by the tides as well, such that right after high tide, there's an event, and right after low tide, there appears to be an event. And so this would be the, so here's the tides as the dashed line, and the velocity going from sort of not moving and then spiking up during an event. And these are captured with teleseismic records. And so what we wanted to explore is why sometimes stick slipping, why sometimes smooth sliding, how is this affected by the tides? We are really curious about this, so we embarked on our second series of experiments. And in this case, rather than that program I showed you before of velocity steps, slide, hold, slides, in this case, we went through, this is in displacement, we have an initial ramp and then two median velocities, but during those medians, there's a bunch of oscillations. So here's the velocity down here, where we've got several oscillations at different periods and amplitudes. And then we have a higher median, and this, again, different amplitudes. And so the response we got was this frictional response. And so let me go to a different view of the same data. So again, this was our forcing routine. This is what we were telling it to do by our program, putting it through these paces with the sinusoidal forcing. And this is how it was responding. This is the friction. And so what I find rather interesting is that in some cases, it's kind of a one-to-one comparison. You know, it sort of does what it's been forced to do. Other times, it seems to barely be modulated by the tides at all at those amplitudes. And other times it has this interesting, I would call this like a slide, hold, slide, like a relaxation curve superimposed on top of a sinusoid. And because I have that sort of elbow in the data, or this, I guess, velocity step we want to point out in every one of these data sets, I have one velocity step with which I can then analyze all of that rate state information and pull that out. And interestingly, because to me, when I first got this data, this seems, I don't know, somewhat random or a surprising response, but it turns out you can use that rate state information and predict it. That if you use a forward model, which is just a very simple elastic 1D slider block, and for the velocity, you put in a sinusoid and you put the rate state formulation equations and the parameters you got from that one velocity step shown here in the inset, and then you run it for these different frequencies and periods. Sorry, that's the same thing, frequencies and amplitudes. Then you can predict a pretty similar, I think it does a really great job of predicting the behavior. But I want to point out that using that one velocity step in the middle of each of my experiments and analyzing for that A minus B behavior, I still didn't find that, you know, the smoking gun. I still always got velocity strengthening behavior predicted by that. Yeah, so the point of this was that a forward model can do a really good job of predicting the experimental work, except when it doesn't. So there were a handful of, one or two really, cases where we actually got big stick slip behavior. And so in those cases, it was unmistakable, it was audible, quite loud. It would happen in some cases right on the cycle, once every cycle at the exact same spot. In some cases, it actually, it would skip one cycle, and so you would have what you call period doubling. And in those cases, the stress drops were huge. So delay in sliding, a larger slip, like in the observations at Whillans. And in those cases, the forward model, which you know, was using using parameters from here, which were all predicting velocity strengthening behavior, it did not predict those big stick slips. And so this motivated Rob. So Rob Skarbek, he created this really great program. It's freely available to analyze friction data. So if you are someone who looks at friction data, please go use that. But he was inspired by the results from the lab to tweak this and to use that same program, but instead now look at the oscillatory data. And so this has a couple of great effects. So one is that he gets a lot more data. So I just had that one velocity step, but he's able to pull out the rate state values from all of those different oscillations at different amplitudes and frequencies. And so he's able to get a lot more data to begin with. And second, and far more importantly, in doing it this way, he's seeing a lot of velocity weakening behavior. And so, I mean, the take home for me seeing that is that perhaps our methodology of looking at velocity steps to describe maybe they're not so accurate for describing a very dynamic system, a system that's perhaps being modulated periodically. And but another exciting thing is that, so now, using just a velocity step is great in the lab, but nature doesn't always accommodate and perform a little velocity step for us, right? Nature is complicated. Nature is doing dynamic forcing. And so by having this program, you can then maybe look at actual dynamic system, actual glaciers that are being modulated, actual faults that are being modulated by the tides, and be able to pull out the rate state parameters. So I guess this is where I want to give a big plug. If you are a person who's holding on to this kind of observational field data that's oscillatory, that's frictional and oscillatory, please reach out to Rod and to myself, and it would be great to incorporate that. So another direction we went with these experiments after doing the oscillatory work is that one criticism I got was okay, well, that's interesting, but most glaciers are not actually sliding on pure rock. There's actually usually a layer of till, this soft deformable beds. And so Seth Saltiel came and did a postdoc. He was one of the postdoc fellows at Lamont, and he did a really nice study of looking at ice on till in between the rock. And actually, in reality, because he wanted to carefully control temperature, he actually used these metal blocks where we can have water going through to carefully control the temperature very near to the interface. But zooming in, the metal had teeth. And so we weren't ever like looking at the friction of till against metal. By putting these teeth in there, the deformation always happened either within the till or at the till ice interface, as you'll see in a minute. And also, in order to compare, he in some cases made a central block where we took the ice out of the situation, and now he's kind of forcing the deformation to happen within the till alone. So when I say till only, those are those experiments. And here are some of his results. I recommend you look up his paper, but in looking at, say, warm temperatures above the melting temperature, here is a till only, with that metal instead of an ice block, versus the ice till. And, zooming in on, here are the velocity steps here, and then here are the slide hold slides over there. But the velocity steps in both cases at these conditions, warm temperatures, you see, we don't have the velocity step analysis itself, but you can see very obviously that with increasing velocity, you have increasing friction. So that is, that's the velocity strengthening behavior. And then we also see he was also very able to measure very modest healing, huge relaxation, but very modest healing of the interface in these ice on till systems. But Something interesting happened though when he went to colder temperatures. So this is, yeah, here's a temperature here showing it's about -3 degrees. And in this case, he did get these nice peaks and that he was able to analyze and pull out the rate state parameters. And, you know, you can see from the data itself, but also when he did the rate state, he actually did determine velocity weakening behavior in this ice till sample that is below the melting temperature at about -3. Also looking at the healing, he saw that I was supposed to point out this circle I had circled on my healing data several slides before, that at the longest hold times, his sample starts to resemble ice healing in my simple ice on rock system. So I guess at short time scales, it was behaving more like the till. Healing was in the till, and then it starts to happen in the ice at long hold times. So I guess I should back up. I said that although he doesn't see stick slips in this experiment, the rate state parameters predicted that there would be velocity weakening behavior, but it turns out at these conditions, the stiffness of the apparatus, it was too high. And so with a little bit of tweaking to the stiffness of the apparatus, he was then able to get, even at these relatively warm temperatures at -3, he was able to get basically stick slips on demand, just a whole bunch of them. And you can see here's the motion of the sample. This is the displacement, and then these are the just full of stick slips, just tick, 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 the right way. You could hear them, and you didn't have to just hear them. He also employed a transducer to measure, like a seismograph, the seismic events for each one of these. And over just a short period of time, he got some tens of thousands of separate waveform events, and he put these through AI. Yes, so he was having machine learning. That's what word I was looking for. Machine learning, trying to identify, to see if we can identify between, for instance, sliding in the till, sliding in the ice. He's working on the revisions for this. So that was really nice to see. And that's just one with one acoustic transducer acting as a seismometer. And so in the future, some of the ways we're hoping to go with this is to have a really better sense of really what's going on at the interface, really using, you know, the state of the art to try to determine the nature of this interface. Where does healing happen? Where does you know, initiation of slip occur during events? So we're going to try to up our game and not use just one transducer, but use a series of them, either in this same double direct shear configuration, or we're also have proposed to try to, you know, kind of change our configuration to this ice horizontally on top of, in this case, maybe a glass plate, where we could use TIR methods to image the change in the area of contact during loading and during friction. So stay tuned for that. That's kind of directions we're hoping to go to. So what do we learn with these series of ice on rock and ice on till experiments? We found that we can use the laboratory experiments to recreate basically all forms of behavior of ice streams, whether that's smooth sliding, stick slip, or, you know, everything in between. We found that healing is very high in ice at these conditions, and it could certainly happen on the time scale of a single. And that, interestingly, that the rate state parameters that we learn from a single steady state velocity step might not be the same as the dynamic conditions. And there's 2 companion papers that discuss that. I hope you'll, oh, this is updated. They're both out now, both 2022. And also Seth's paper, identifying velocity weakening, is out in 2021. So some of the things we still want to do, I put out that big plea of, like, if you have observational data, we would love to work with you and to use the rate state formulations to provide more predictive modeling. So please reach out. We also are hoping to use this AE data I know there's not a one-to-one correlation between acoustic emissions in the lab and seismic signals, but there's some relationship there, and we're hoping that we could provide shed some light on that. Now, in the last few minutes that I have, I won't take very long on this, but I wanted to give you a little teaser about what happens in ice friction when you go to even lower conditions. So there are moons of the outer solar system, for instance, Europa, the second of the Galilean moons of Jupiter, where there's an icy shell above a liquid ocean. The icy shell goes from a temperature of about 70 or 80 K all the way down to the melting temperature. So it's a huge swath of homologous temperature space. So it, as such, it's very much like rock on Earth, behaving kind of this brittle ductile transition. You can, think about your lithospheric strength envelopes and stuff, but also there are a whole bunch of faults and fractures and things on the surface, some of which have these offsets consistent or suggesting that you've got some strike slip faulting there. So we wanted to explore, like we know on Earth about the distribution of frictional behavior with depth. We are hoping we can do that with temperature. So this is Earth now, thinking about laboratory experiments on rock and fault gouge have determined that there's this kind of distribution where at shallow conditions, that A minus B, that velocity strengthening behavior is here at the surface, but then with depth, there's this velocity, this swath of velocity weakening behavior before it transitions back for ductile behavior deeper on. And this was found that not in every case, not in all situations, but a good number of earthquake source regions happen in this so-called seismogenic zone. So what we wanted to know is if this could happen on these icy moons where there's this really huge thermal gradient. And just a little teaser. Mahi Zaman, he's the grad student working on this, did beautiful experiments from this whole temperature range. And just want to share this beautiful data that he's got. He reported this at AGU, but he's also going to submit very soon. And indeed, with just temperature alone, we see that same kind of behavior where we have velocity strengthening, velocity weakening, and strengthening again. And so I think that's pretty exciting because if you're going to plan a lander mission, for instance, and you want to put a seismometer package on the foot of this lander, you want to hope that there's going to be events. And so our research has shown at least the conditions are right, that you should have velocity weakening, you should have a source region for earthquakes on these icy moons. And some of the current work we're doing is just trying to look at all of this, really nice stick slip data that he got in the lab, and trying to, pull out things that help tune seismometers, help give you values for instance, recurrence interval and stress drop at different conditions. So stay tuned for that. Those are new projects coming out. And just wanted to say thank you. The Rock and Ice Mechanics is a fun place to be. We have lots of interns that come through. It just being able to work with rocks and ice in this very tactile way is a great educational tool, I find, and I have a lot of fun.